All right, welcome to Newton's third law. And the big thing that happens with Newton's third law is that these forces are not, these systems are no longer isolated. That's why I say not isolated anymore. So we're going to describe the motion of objects that are interacting and how those forces kind of work together. So I have a few notes up here. When two objects interact, the forces always exist in pairs, so an action force and a reaction force. The reaction force always acts on a different object than the action force does, and the reaction force always acts in the opposite direction. So you have the force A on B is equal to the negative FB on A. So that is, this one is the action. This one's usually the reaction. Action-reaction forces can be with objects in contact within each other, such as a tennis ball and racket, or action-reaction forces can also be an object not in contact with each other, such as a magnet, nail, or between the Earth and Moon. Or even, like, if we're talking about somebody skateboarding, you have your reaction force and you have your action force and how they kind of play together. And it can be really simple. Like if you have somebody who is bumping a volleyball, you have a force here, your force action, faction, and that is the force exerted by the player. And then you have the force by the player because they are pushing it outwards. But then the ball, what it's trying to do is it's trying to also force reaction. This is the ball on the player. So it's trying to push backwards against it. And it's only at the moment of collision. That's a kind of a key thing to remember there. Even like when we're thinking about this one, the Earth and the Moon, or between gravity and such, you can have something falling. This is your F action. And then you have your F reaction. And this is the ground. So this is the force that is pulling down. This is the earth pull. And then this is the resistance of the object. So kind of thinking always of it in those pairs and like justifying what those pairing groups are. And you can see like that one is interacting going towards each other. This one is interacting going away from each other. This example of a magnet and a nail, same thing. So if I have magnet here, it's going here, and I have a nail here. Excuse my drawings. And it's getting pulled in. So this is the F action, and this is the F reaction. And they're both heading towards each other. And it's talking about like how these objects are accelerating towards each other. And you can definitely do this in the gym if you guys still have like those little boards that have wheels on them and you sit on them. So choose somebody who's about the same weight as you, sit on those boards, and then push with your feet against each other and just see what happens. So if you're interested in seeing how that is, absolutely is a great idea. But let's jump into this example. Let's apply the law to situations involving frictionless surfaces. So we don't have to worry about resistance stuff. We just have to worry about these kind of action forces and reaction forces. So we have three boxes, A, B, and C, are positioned next to each other on a horizontal frictionless surface. This one. An applied force is acting on box A, causes all the boxes to accelerate at 1.5 meters per second squared to the right. Calculate the force exerted on box C by box C on box B. Yeah. So let's think about what we're given here. We have some masses. squared. And then what we're looking for is we want the force of C on B. This is all supposed to be subscript, but my pen is only one size here. So let's think about a free body diagram. Let's get our little compass. We're going to designate positive, positive, negative, negative. So we know, like, man, that is a terrible looking positive. Let's try that again. So free body diagram just for C, because that's what we're worrying about right now. So if I draw this free body diagram, and this is box C, I still have my Fn, my normal force. I still have my force of gravity. But I also have this force, Fb on C. Now, let's think about this. Box C is not accelerating up or down. It's accelerating the horizontal. So because it's accelerating in the horizontal and not in the vertical, we know some things. So because it's not accelerating vertical, we can say that the F net is equal to 0 n. But this is only in the y direction. And that's just important to know, because now we know that we don't have to do vertical direction calculations. But our F net in the x direction, the horizontal direction, we're worrying about this FB on C. Horizontal. So we have the F net. You can call it H or X. I'm probably going to go X because that makes more sense to me, is equal to FB on C. That's one big subscript. Remember that. So let's apply Newton's second law. This tells us a few things. So FB on C, we have F net is equal to mass times acceleration. Excuse me. Just had to sneeze there. So this is FB on C is going to equal our mass C acceleration. F bonk. So then our mass of C is 5 kilograms. Our acceleration is 1.5 meters per second squared. This is all good because this is going to give us the values that we need for newtons. And that's going to give us 7.5 newtons to the right. Now, I know what you guys are thinking. This isn't quite what the question asked of us. The question asked of us, force exerted by box C on box B. And this is B on C. We need C on B. So we need the opposite reaction. They exist in pairs. So this is of the force pair FB on C is equal to FC on B. But this is happening in the opposite direction. So if I want to know how these two boxes interact with each other, so I have C and I have B. If I'm looking for how this B on C, reacts this way, right? But if I want C on B, I need the negative of this value, so it has to go reverse. So that's why this is now negative in order to find the third, like the opposite. So this is applying the third law here. So then this just means that it is 7.5 newtons to the left. So it's just the opposite way because we're pushing the opposite way. I hope that makes sense. If it doesn't, please ask. We got one more example today, and this one involves friction, so it's another box problem. We're going to have 2 boxes, again, instead of 3, of identical material but different mass placed next to each other on a horizontal rough surface. An applied force acting on box A, so we have a force applied right here, and it causes both boxes to accelerate at 2.6 meters per second squared to the right. If the magnitude of the force of friction is 28.3 newtons on box B, calculate the force exerted by box B on box A. So what do we know? We know our mass of A is 6.5 kilograms. Our mass of B is 8.5 kilograms. The force of friction on B is 28.3 newtons. Force of friction acts in the opposite direction, left, and your acceleration is equal to 2.6 meters per second squared. What we want to find is FB on A. So let's find this free body diagram for B. Of course, we're going to have our Fn, and we're going to have our Fg. Those guys just operate in pairs together. We're going to have the force of friction. And then we're also having this force of A on B. So we got a pretty hefty amount of stuff happening here. Same thing as before. It's not accelerating up or down. So no vertical calculations. Let's look at our F net in the x direction though. F net x. So we have 2 things happening in opposition of each other here. We have our force of friction, we have our FA on B. This really should be F. No, this is force of friction on B. I just need to write it out better. So then we have our FA on B plus your FF on B. So we need to find our FA on B. We need to find this guy because that is the opposite force that is happening over here. F net is mass times acceleration. So let's start sliding some stuff around. If I want to find this, I'm going to inherently move this F on B over. So it's just going to be F net X minus F on B, F A on B. So then our F net is our mass times acceleration. So our mass in this case of B is 8.5 kilograms multiplied by 2.6 meters per second squared. minus 28.3 newtons negative is equal to FA on B. This makes sense. This will give us newtons. This is in newtons. So we're going to plug this into our calculator, and you're going to get 50 newtons is equal to FA on B. And then we're going to apply the third law. Which is the equal and opposite. So FB on A is equal to the negative of this value. So it's equal to negative 50 newtons or 50 newtons left. So it seems counterproductive to solve for the opposite of what you're solving for, but you're solving for what you can given what you've been given, and then you're just flipping the opposite of it by applying the third law. I hope these examples were helpful for you. If you need some more additional help, please ask, but past that, good luck on your assignment.